Hi everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking to you about what wall functions do I need for Epsilon, the turbulence dissipation rate. So just to start with an overview of what I'm going to talk about today, I'm going to start by explaining how the wall treatment for Epsilon is different to the wall treatment that we use for velocity and for temperature. Then I'm going to move on to look at what wall functions do we use specifically for Epsilon, and then I'm going to finish off this talk by talking about how we account for boundary cells that have multiple boundary faces. So a cell with multiple wall faces, which I haven't considered yet on this channel. So I'm going to start off with a brief reminder of what we've already been through. On this channel I've already covered the wall treatment and the wall functions for the velocity and temperature fields, and I'm going to put links in the description below this video to those videos so you can go back and remind yourself of the wall treatment that we use for velocity and temperature. And then in today's talk I'm going to talk to you about Epsilon and how Epsilon is different to the velocity and temperature fields. So just a brief reminder of what we do for the velocity and temperature fields. We have our boundary cells, which are the cells in contact with a boundary, which you can see in the diagram below. And as a user of the CFD code, the user will specify the boundary values for the velocity and temperature. So these are going to be U sub W for the velocity field and T sub W for the temperature field. So the user specifies the values at the wall ahead of time before the simulation begins, and then the CFD solver will proceed and solve cell by cell and compute the values UP and TP at the cell centroids. Now, in a standard CFD finite volume code, the variation of quantities across cells is linear. And this creates some problems for the wall adjacent cells, because if the cell is too large and we assume that the variation between the wall and the cell centroid is linear, that will often mean that we calculate the gradients wrong, particularly if we have a turbulent flow field where the velocity and temperature gradients at the wall are very large. And if the cell is too large, so not in the viscous sublayer, then we'll calculate the wall shear stress and the wall heat transfer incorrectly. So what CFD codes do is, for velocity and temperature fields, the wall functions for velocity and temperature modify the near wall thermal and momentum diffusivities. That's nu sub-effective and alpha sub-effective there. So what that allows us to do is to use equations 1 and 2 to compute the wall shear stress and the wall heat flux by assuming that the variation across the cell is still linear, but we modify those diffusivity coefficients so that we get the correct wall shear stress and wall heat flux. Now, that's the treatment that we use for the velocity and temperature fields. However, the turbulence scalar fields require a different treatment, and that's what I'm going to focus on in today's talk. And the reason the turbulence scalar fields are different is because you may have noticed in some CFD simulations of your own that the user isn't requested to specify the value of the turbulence scalar fields at the wall. So you don't have to specify a turbulent kinetic energy, a dissipation rate, or a specific dissipation rate at the wall. Usually the user simply informs the CFD code that this is a wall adjacent cell and we'd like to use the turbulent near wall treatment. And what that means is that the CFD code has to be set up slightly different for the turbulence statistics, because we don't know the value of epsilon sub W in the image there. So the entire method of wall treatment that we use for these turbulence statistics is going to be different to what we do for the velocity and temperature fields. So in this talk, I'm only going to focus on epsilon, which is the turbulent dissipation rate, and I'm going to be doing separate videos for the turbulent kinetic energy, K, and the specific dissipation rate, omega. And before I get started, what I'm going to do is just clarify and give a brief reminder about how we treat boundary cells. And then we're going to look at how we develop wall treatment methods for epsilon. So the first and perhaps most important thing we need to think about is that a boundary cell, as you can see there in the diagram, may have multiple boundary faces. So for example, the rectangular cell you can see here is connected to walls on boundary face 1 and on boundary face 2. And of course, for a general n-sided cell, the boundary cell could have multiple boundary faces. And if we really stop and think about this, what it means if a boundary cell has multiple boundary faces, it means that we're going to have a different value of y plus on each face. So as you can see here in the diagram, the y plus value for boundary face 1 is much smaller than the y plus value for boundary face 2. And as a result, the turbulent and momentum diffusivities are going to be different on each face. So the method that we set up here for epsilon has to be able to allow for cells with multiple different boundary faces. And the treatment that we used for velocity and temperature fields was consistent with these boundary cells, as we just compute a different nu and alpha on every boundary cell face that is in contact with the wall. But for epsilon, we're going to need slightly different treatment. So I should bear in mind here that one cell may have multiple y plus values associated with it. For this reason, the y plus is associated with a cell face rather than with a boundary cell. And this will become a bit clearer as I move through the slides. So the way we assess boundaries in CFD codes is that we proceed along the boundary faces one by one. So we don't move along the cells, we move along the boundary faces. And in this diagram here, what you can see is that we'd start on cell 1 on the left, and we'd work out our y plus value and then our momentum and thermal diffusivities, and then we'd move to boundary face 2, again repeating the process, and then onto boundary faces 3 and 4. And these boundary faces share the same cell, but we still evaluate the y plus and the momentum and thermal diffusivities on each boundary face one by one. So it's definitely worth bearing in mind here that we move along boundary faces rather than on boundary cells, and that's what we're going to do as we move through the process here. So what about epsilon? How is epsilon different to the velocity and temperature fields? Well, the short story is that we calculate the value at the cell centroid, that's epsilon sub p, directly. So we aren't modifying or computing gradients as we were with velocity and temperature, but actually we're going to compute that value at the cell centroid directly using a wall function. So we calculate epsilon sub p. And of course, that now means that the CFD code doesn't actually solve the Navier-Stokes and turbulent scalar equations in the wall adjacent cells, because we're going to assign those values directly using wall functions. So that will of course mean that the matrices will have to be resized for the epsilon equation, and we're going to calculate that value epsilon p directly using our wall function. It's a completely different approach to velocity and temperature. And the reason that we take this approach with epsilon is that epsilon, which is the turbulent dissipation rate in that wall adjacent cell, needs to balance the production of turbulent kinetic energy in the cell. And the production of turbulent kinetic energy is a source term that you see on the right hand side of the turbulent kinetic energy equation, and similarly to all source terms are evaluated over a volume or over a cell. And so in order for us to ensure that the dissipation rate, epsilon p, balances that production of turbulent kinetic energy in the wall adjacent cell, we calculate the value of epsilon at the cell centroid directly. And this is the reason that we use a different treatment for epsilon. But what value are we going to assign epsilon? That's what I'll show you next. So, as you might remember from the previous videos for velocity and temperature, what we do is we start by looking at the universal behaviour of the quantities normal to the wall. So the plot on the right, which you may recognise there from our previous video, is the variation of the dimensionless velocity, u+, plotted against the dimensionless wall distance, y+. And the black line is data from direct numerical simulations, or the true variation of the mean velocity field normal to the wall. And you might remember that the standard approach to represent this variation of velocity normal to the wall is to fit wall functions to it. So we fit a blue curve in the viscous sublayer, that's a y+ less than 5, we fit that blue curve, and then in the log law region, that's for a y+ greater than 30, we fit that green curve to the DNS data. And it's those blue and green curves that we put into our CFD codes and allow us to treat velocity normal to the wall. Now, you've probably seen plots like that for the velocity field. They're quite common in the literature and crop up in quite a few textbooks and user manuals. But of course, as well as a variation of velocity normal to the wall, we also get a variation of the turbulence dissipation rate normal to the wall from the DNS data. And the variation of epsilon is given there on the left. And you probably haven't seen this plot before, but it takes a very distinctive shape. So we can see that at the wall, the value of epsilon plus is around 0.26, and moving away from the wall, the dissipation rate reduces. We have maximum dissipation at the wall. As we move away from the wall, the rate of dissipation decreases in the viscous sublayer, and then increases and reaches a peak in the buffer layer. And the reason for that is because the production of turbulent kinetic energy is a maximum in the buffer layer, and so the dissipation rate is also going to reach a maximum. And then moving further away from the wall, we see again that epsilon continues to decay as we move further away from the wall. And this is the real behaviour of epsilon normal to the wall, and we're going to fit some functions to that, and then we can use those functions to specify the value of epsilon at our cell centroid in our CFD solution. So depending on how far away the boundary face is, the boundary cell centroid is from the wall, we can work out what value of epsilon we should apply there using the DNS data. So what functions are we going to fit to epsilon? Well, as before, we fit a blue line in the viscous sublayer, and we fit the green line in the logarithmic law region. And the data fits, which I'm not going to go into detail here, but I'll provide a link in the description below to a very useful paper which you can read, which explains how you derive and fit these empirical profiles to the DNS data. And what they are is equation 3 is epsilon is 2k plus over y plus squared. So as y plus increases, epsilon drops off rapidly away from the wall. And then we have a green line for the logarithmic law region where epsilon plus drops off a bit more slowly, which is just 1 over kappa times by y plus. And we can see again that in the intermediate region, in the buffer region, much like the velocity and the temperature treatment, this segregated approach doesn't match the value of epsilon well. So some CFD codes may choose to use some form of blending in the buffer region, or may simply just switch between the two computed values of epsilon. And that will of course vary code by code, but for the user, this is another reason why it's generally recommended for you to have your cell centroids either in the viscous sublayer with a y plus less than 5, or in the logarithmic region with a y plus greater than 30. Right, so we've got our two functions. These are two dimensionless functions for epsilon plus, but what is the actual value that we're going to apply at our cell centroid for epsilon? The first thing we'll do is we'll look at the solution in the viscous sublayer, that's equation 5, and then we will substitute in the real quantities for epsilon plus, k plus and y plus, And that rearrangement you can see there in equation 6. We've substituted for epsilon, for k plus and for y plus, and then cancelling terms and rearranging, and we arrive at equation 7. So epsilon sub p, the epsilon at the cell centroid, is equal to 2 times the turbulent kinetic energy at the cell centroid, kp, multiplied by the laminar momentum diffusivity, divided by y squared, where y of course is the distance normal to the wall from that boundary cell face to the centroid. And that's the value we'll apply at our cell centroid if the cell is in the viscous sublayer, and then we use the same, do the same thing again in the logarithmic region. And so starting off with equation 8, epsilon plus is 1 over kappa multiplied by y plus, and if we substitute in the dimensioned quantities for epsilon plus and y plus in equation 8, and we do some rearranging, we arrive at equation 9. So if our cell is in the logarithmic region, then epsilon sub p is equal to the friction velocity, u sub tau cubed, divided by kappa times by the distance yp, that's the distance normal to the wall again. Now, if we want to make any further progress, it's important to note here that we're going to substitute u sub tau for the equation shown in blue there. That's c mu to the quarter times by the square root of the kinetic energy, the turbulent kinetic energy. And a few of you may of course realise and note that this is a different method to what's conventionally applied, which is the equation shown in red, which is saying that the friction velocity is based on the square root of the wall shear stress. And this is a very important distinction for the wall treatment of epsilon, that the friction velocity, u tau, is based on the square root of the turbulent kinetic energy at the cell centroid rather than the wall shear stress. And this approach is sometimes referred to in the literature as the approach using y star rather than y plus. So an approach using y star uses the square root of the turbulent kinetic energy for the friction velocity, whereas the approach using y plus uses the square root of the wall shear stress. And without going into further detail about that, if we substitute in the blue equation into equation 9, then we arrive at equation 10 there. And this form of the value for epsilon at the cell centroid is the one that you'll often see in a lot of CFD user guides and user manuals. And CFD user guides and user manuals don't tend to provide the solution in the viscous sublayer, and the reason for that is it's assumed that if we're using the K epsilon turbulence model, that all of our cells are going to be in the logarithmic region, because the K epsilon model wasn't originally designed for use in the viscous sublayer. So that's often why you'll only ever see equation 10 quoted in CFD user manuals. So what about cells with multiple boundary faces? Because the approach that I've shown you there is computing the value at the cell centroid directly from the boundary cell face. But what if we have cell 3 as shown in the diagram? So the red cell, cell 3, has 2 boundary cell faces, and each of those boundary faces is going to compute a different value of epsilon sub p. So what value do we use at the cell centroid, particularly as one boundary cell face might be in the viscous sublayer and one might be in the logarithmic region, depending on the shape of the cell. So what do we do for cells with multiple boundary faces? The short answer is we take an average approach, so we average the computed values for each of the boundary cell faces. Now, the way CFD codes do this in practice, and the way you'll see it referred to in user manuals, is CFD codes assign a weight to each boundary cell face. And what a weight represents is the fraction of that boundary cell that has boundary cell faces. So in the diagram here, if we move along starting at cell 1, we can see that cell 1 only has one boundary cell face, so that face is assigned a weight of 0. Move to cell 2, again that cell face is assigned a weight of 1, but then when we move to cell 3, we see that cell 3 has 2 faces, and what that means is that each of those faces is assigned a weight of a half, or 1 over n. and the same weight is applied for each of these faces. We use a half and half. We don't use a 0.25 and 0.75. CFD codes as standard will assign the same weight to each of those faces that make up the boundary cell. So we can then see that if we compute the value at the cell centroid based on the values of each of those faces, we're going to get a contribution of a half from each of those boundary cell faces, which is the same as averaging the value we compute at the cell centroid. So now let's wrap this all up and look at the overall algorithm and process we use for computing Epsilon. The way we do it is we move along every boundary cell face again. So we move along the boundary cell faces, and for each cell we add a contribution from that boundary cell face to the boundary cell centroid that that cell is associated with. And depending on whether that boundary cell face is in the viscous sublayer or in the logarithmic region, we add a different contribution. And that will be given by either equation 12 for the viscous sublayer or equation 13 for the logarithmic region. And we can see here that the contribution is multiplied by the weight, Wi, which of course if the cell only has one boundary cell face is 1, and if we have more than that it will be 1 over n. And it's important to remember as we go through here where the variables are stored. So Kp, the turbulent kinetic energy, is stored at the centroid of the boundary cell itself. However, the weights, the momentum, thermal diffusivities, and the wall normal distance, y, are stored on the boundary cell faces. And that's important to remember because each boundary cell face may have a different wall normal distance, different y plus, different shear stress. So hopefully with this treatment, moving along the boundary cell faces should help clarify how walls are treated in CFD codes for Epsilon and for all the other quantities. So just a quick summary before we finish. The wall treatment for Epsilon is different to that of velocity and temperature. With Epsilon we compute the cell centroid value directly, whereas with velocity and temperature we modify the momentum and thermal diffusivities at the wall. And because the value at the cell centroid is computed directly, we use weights to account for boundary cells that have multiple boundary faces. And of course, because the CFD code now doesn't compute Epsilon in those boundary cells, we have to manipulate the matrices to account for those cells not being included in the computation. So I've got a few useful references here for you if you'd like some further reading. The ANSYS Fluent user manual is always a very useful source for a quick browse and a reminder of how these wall functions work. And the section you're looking for is 12.10.2, and of course there's going to be a link for that down in the description of this video. And a very useful paper for those of you who'd like to dive into this in a bit more detail, perhaps look at the DNS data and maybe look at the derivation and fitting of those wall functions themselves. It's a very useful paper by Kalitzin et al. In the Journal of Computational Physics, and I've put a link also for that paper down in the description below for those of you who'd like some further reading. And of course for those of you who would like a reminder on how we treat the velocity and temperature fields, I've also linked videos to my 2 previous videos for velocity and temperature down in the description below. As always, thank you for listening, and I look forward to hearing your comments in the description below. Until next time.